So I'd like to go through the structure of a collision in 2 dimensions. I'd like to go through how you actually simulate this collision in the computer. So when you run your game, you're going to have basically 2 phases. You're going to have no collision and a collision. And I'd like to go through everything in that except the mathematical part. The mathematical part I have some other videos for. It's a little more complicated. Go ahead and look at those when you get to the point where you think you need them. But right now you have a more general overview. So what I'm going to do is I'm going to go through, I'm going to talk about collisions, and I'm going to show you what a collision should look like. And then I will go through and show you how we simulate the collisions, the way I'm going to have you simulate the collisions here. And again, that'll include what happens before the collision, what happens after the collision, and a high-level view of the innards of the collision. All right, that will also include a flow chart so that everything is a little bit nicer for you when you think about it. Now, the collision we define in the collision is different from the deflection. So we've done the deflection twice. We've done it once for a ball hitting a wall, and we've done it once for a ball hitting a peg. And that's in 2 dimensions. In 1 dimension, we've already done the deflections and we've done the collisions as well. But in 2 dimensions, we've done deflections so far, and now we're going to do the collisions. In that case, in the deflection, you have 1 immovable object and 1 movable object, basically. In the collision, you have 2 movable objects. So 2 things are moving, they hit each other, and they reflect off of each other. They bounce off of each other. So that's what we're going to do. Instead of having something bounce against a static object, we'll have 2 objects bounce against each other and often move in whatever directions they want to move. So let's start that out just by showing what happens, right? The physics of the situation is twofold. The first thing is that you have uniform motion, something just moving along, translating freely until it actually hits something. At that point, you have a transfer of momentum along the line of impact. It's very straightforward. Either nothing's happening, or there's no interaction between the 2 objects. Then all of a sudden there is an interaction between the 2 objects, and then they don't care about each other anymore. So that makes life easy. We only have to worry about their interactions every once in a while, depending on what the simulation actually is. So in this case, what we do is we translate by updating the position of the object by the velocity. So those arrows represent velocities. The dark circles represent the current positions. The light circles are where they're actually going to hit. So I step through this. You see they move again, they hit each other, they're going along this line of impact, and now they move in some other direction, and that's your collision. That's all there is to the collision. This is pretty much what's going on. It's not exactly what's going on because the blue ball actually goes a little bit slower. So let me show you an actual simulation. So this is a simulation. This simulation here is based on the in-class exercise that I'm going to have you do. I've just moved the blue ball around a little bit, and I haven't changed the color of the yellow, or I haven't changed the color of the cue ball, but that's okay. So you're fine. But when I press the space bar, these things are just going to move, and you'll be able to figure out what's going on. You can see how this looks exactly like what I showed you in this slide before. And there's an error. And now it's just being mean. Okay, there we go. Bang. See, so it looks exactly like what I detailed before on there. So you saw this. The blue ball came by and then it reflected off. It came in at a 45-degree angle because I programmed it to, and it came off at some angle that was a little bit off of being perfectly horizontal, and they hit it just about this angle. Took me a little while to make it hit exactly like this drawing, but that's okay. That's what we got. So this is the ideal collision. That is, this is what the analytical solution would look like. If I went through and I calculated everything, I figured out exact positions and all these other things, this is what would actually happen. This is what I'd pull out when I drew it. What we're going to do is we're going to simulate it, which means we're going to start with the initial conditions, some initial positions, and we're going to step through what happens, right? So we start with these initial positions, we have these initial velocities, and then we go for one time step, and we move the objects by their velocities, right? So that they move just so far. So that is how we're going to handle uniform motion, like we have been handling uniform motions. We just update the ball position by the velocity that is stored in the ball, and the time, the simulation time, how the time step between steps. And we actually measure these in our simulations. Our real-time simulations, we measure the time step from the computer's clock. So I've updated those positions. The next thing to do is just to go ahead and check, right? Well, has there been any collision? And at this point, no, there hasn't been any collision. They're not going to hit each other till they get to that parallelogram over there, that blue-green parallelogram. That's the intersection of the blue and the green tubes. So I've asked myself on the flow chart, do they overlap? I say no. So I just move on and go back. So you'll notice that I say pass here. So if the blue ball hits the green ball, right, I pass. Well, I don't really pass. That's something I'm going to tell you about when you're older. You know, a little bit later, when you're a little bit older, when you're ready for it, when you're a more sophisticated, mature person, we'll talk about what goes there. But right now, we're just going to ignore what happens there because the blue ball does not hit the green ball, right? So we ignore that, and then we go back to the beginning and update the ball positions again. The balls get closer to each other, but they still don't overlap, right? So we do that again, and when we do that again, now they overlap, which means that there's been a collision. Okay, so that's how we actually figure out if there has been a collision, is that these two balls overlap. So that's not allowed. We don't like that. So what we do is we start our collision algorithm, right? So now we're going to do our green ball collides with the blue ball, and we could do it the other way. We could do blue ball collides with green ball, but I like having all the alternating colors, so that's the way we did it. They both of the balls have all of the same methods inside of them, so it doesn't matter which way you do it. So now I've said that the two balls have hit each other. I have to go through the collision resolution algorithm, and when I do that, the first thing I do is I send the balls backwards. All right, I send them backwards in time by dt. All right, and I call that rollback. And what that does is it gets us away from this point where the two balls overlap. That can be bad because that leads to certain simulation errors where the balls get stuck inside of each other, and you don't want to do that. So you move back to the previous step before there's any overlap. All right, and when you do that, you go ahead and use the centers as the line of action. The centers of these two balls is what you're going to use for the line of action. You can see that in the other video that I was talking about, the other video for Lecture 17. That's on YouTube. That's at this address that's on your screen now. And then you can just go back to... So you do that, you change the directions according to the physical laws. Okay, so we have physical laws governing the collisions. That's what we're using this collision algorithm for, is for those physical laws. You resolve the collision between the blue and the green balls in this change velocities function. You could use a method that's stored in the balls as well. That's what we actually do in the simulations, but it's also fine just to use a function. It's perfectly okay. There's no reason to say one ball is better than the other ball, right? So now we've changed the velocities, but we're still one time step back, right? We're still in the past. We're sitting on point 2, even though we've already gone to 3, right? So before we go back to the normal workings, we're going to have to go forward in time one more time. I went backwards. So now we've updated the ball positions. We're in our normal spot, and that's all we have to do for our collision algorithm. It's ready. The balls are ready to go and be updated and simulated in line with everything else that is going on in your game. Okay. So once you've done that, you keep on going, and you go back and you update the ball position, then check for overlap, then you update the ball position, then you check for overlap, then you update the ball position and you check for overlap, and pretty soon they're off the screen and you don't have to worry about the balls anymore. Everything's done. You've done everything you need to do, and you have a working collision routine. So that's all you really need to do in this particular case. So just think about it this way while you're trying to program what you're doing. So let me just go over what the collisions look like again. Right, let's look at it as far as the ball is concerned. First, you can see where the balls are in these two positions. You'll notice that this angle is a little bit different. It should not be, right? But that's an artifact of this rollback. All right. So the rollback goes to the previous time step that is just a little bit off of what you'd have for an analytical solution. In general, since we're going to have DTs on the order of 30 milliseconds, this isn't going to be much of a problem. All right. Where they hit is going to be very, very close to wherever they step back to. However, if you're doing something where you have strong fields, like you have two charged particles that are coming close to being in contact or something like that, you might need to do this in a more systematic fashion and actually solve for the positions of the two balls when there's a collision. That's okay. That's not much of an issue. It's something that you'll have to do analytically and then put whatever that formula is into your simulation. It's a little extra work, but trust me, when I tried doing this with electric field or electrostatic particles and running around having them interact with each other, things got crazy really fast if I used the rollback. I had to go and do the analytical solution. Again, not hard. It's something that anybody who's, say, a sophomore or junior in high school should be able to do with a little bit of work. And if you're a graduate student or a professional, you should be able to do it with a little bit of work. So, it's just work. It's not something that's going to it's not something that's really difficult conceptually. It's just something that you have to be really careful while you do it. So, once these guys hit, they go off on their own and they never see each other again. Everything's wonderful. With the flow chart, the program flow is basically you're in one loop, the update overlap loop. Most of the time you're updating the ball positions and you're checking to see if they hit anything. Usually they're not going to hit anything unless you've got a really, really strange thing going on, but usually things aren't hitting each other all the time. In a game, you want people to have some time to react before all the stuff happens to them, right? But every once in a while, they do hit, and then they go in this outer loop, and this outer loop is your collision resolution algorithm. You step back one time step, you do all the physics that's in this other video, then you go back to the original time step so that you're in line in time with all of the other objects in the game, and then you go back to the inner loop, the update overlap loop. So that's all you're going to really have to do when you're programming objects that can hit each other. I hope that was sufficient for you. It seems to be pretty reliable to me. I'll see you around soon. Bye now.